Yeah. So it's good to be back. Right. So last time I motivated having a six-functor formalism in rigid analytic geometry in order to prove statements like functor or p-cohomology in rigid varieties. And I also said that one of the main issues there was that these cohomologies, at least on non-proper spaces, tend to be infinite dimensional. And in fact, they contain some stuff that comes from the base field. The proposed solution I have is to replace italic p sheaves by some sort of quasicoherent sheaves. And well, the answer, well, at least one big step towards the answer is what I want to do is I want to associate to a space X, maybe with a chosen Claudian uniformizer, but I guess we can mostly think of this just as being P, if you want, or P to the N. I want to associate to it the category of OX plus mod phi quasicoherent modules over the ring OX plus mod phi on my space X. And well, of course, it's not so clear what it means to be quasicoherent over that. And as I said last time, you can't hope, if X is a rigid variety, for example, you can't hope to define this directly on the topology of of X, because locally the sheaf is not acyclic. But as I pointed out last time, when we pass to perfected covers of our space, then this thing does become acyclic. So you can hope to define a good notion of quasicoherent sheaves locally in the pro-étale or V topology. And that's exactly what we're doing. So I associate to any V stack on a perfected space, on perfected spaces. So for example, rigid variety, I associate this category and I define it by gluing so that on nice and finite perfected spaces, it is literally just the category modules over that ring. Oh yeah, sorry. So this is A. This means, okay, I think last time I didn't say it. Like in this primitive comparison theorem that I stated last time, I only said that there's an almost isomorphism between two things, right? And it turns out that, like, in order for all of this to work, I mean, this is no accident. In order for all of this to work, I have to carry this almost stuff through everything. And this little A here, so this means that I localize at almost isomorphisms. So in other words, I invert all the maps in the usual solid category, which are almost isomorphisms. There's a formal way to do that, and that category is not so bad, actually. Okay, one bad thing is it doesn't have complex generators anymore.
What is the bad thing?
It does not have complex generators anymore. But apart from that, yeah, I don't know, like the inclusion into, I mean, this thing has two fully faithful inclusions into solid. Or okay, maybe just ignore that for the most part.
Sorry, can I ask a technical question maybe about to address this? So if we ignore the solid for now, and if we just took the almost derived category of A plus mod phi,
yes,
as a classical almost map, then is the theorem is still correct?
Yes, and easier to prove.
Easier to prove. But you would not have the six functors in that context.
Okay, thank you. Right, yeah, maybe I should very briefly draw what the square means here. So I'm taking modules over that ring, but I'm equipping them with some sort of topology or more like precisely condensed structure. And the square means that that topology is supposed to be complete in a certain sense. Okay, so the ring itself is discrete, of course, but I allow modules which are non-discrete. And I guess like the ones you should think about is maybe products and like products of copy of this guy with a product topology and stuff you can build out of that using fiber sequences. That's essentially all you need to make these things work. Okay. Right. So, well, I have now defined this fancy category. Now I can do that. I have now defined this fancy category, but what I actually wanted to study is italic p cohomology. So I don't really care about these things too much, but I want italic p sheaves. So I think before I introduce six functors for that thing, I should explain how you can get back to p sheaves. So let's say something about the relation. P sheaves. Okay, and the first observation you can make is, if I find my, okay. The first observation you can make is that there is a natural functor. Okay, maybe. Okay, we consider whole subcategory. So this is again maybe for technical reasons, or I guess I can mostly ignore the difference, but I'm only working with étale sheaves, which are overconvergent. Of overconvergent. Étale sheaves. Okay, and this overconvergent, that's just saying that whenever you have a specialization in your space, then the stalks at all of the points of the specialization are the same. And you might think that in scheme theory or in algebraic geometry, that's a very harsh restriction on your sheets. But turns out that in this setting, it's actually not such a big deal.
Can you write the definition of overconvergence?
Okay, so the definition is after pullback. Pullback to any sparse AC plus mapping to X. Okay, so if I have an étale sheaf on X, I can pull it back to any space of this form where C is an algebraically closed field and C plus is an open bound evaluation ring. And this space is just a chain of points. So you should think of this maybe as an analog of evaluation rings. I mean, this C plus is literally a evaluation ring. I want this to be, and this thing to be constant.
What is the evaluation ring here?
This C plus. So this is an open bounded evaluation ring inside of C. Okay, so these are kind of the building blocks in analytic geometry.
So here, to understand that the definition, it is probably important to stick to Huber's foundation. But otherwise,
Yes.
and since I was brought up on space, rigid spaces, I cannot understand what's going on. This is my problem, of course. But is there anything that can be explained to?
Right. I think most importantly, any local system is in there. So this contains. All local systems.
Maybe sort of a related question, like is there a description of this condition of being overconvergent in sort of classical terms, like if you're on a classical rigid analytic variety, is there some way of saying explicitly what it means to be overconvergent?
Probably.
I think there was this paper of the spaces, and I think the space. Well, I think like this was like one of the issues that like rigid geometry that I think of points in topology.
Yeah, I mean, probably this. Sorry, I don't know. Yeah, I mean, it's not too big of a restriction. Like the stuff you maybe care about is in there anyway. What you cannot do is.
Is it a technical restriction for us, or is it something which you have to impose?
I have to impose that.
You have to.
Yeah, and I will maybe make a remark why I cannot go here. It's very weird. Okay. Okay, and then there's a base chain functor. taking your favorite FP sheaf and tensoring it over FP with OX plus maybe A5 going from P at X of P to category. Okay, and now here it's already very useful to have the overconvergent version, because how do I construct this? Well, both of these sheaf categories satisfy the descent, so in order to construct this functor, I can do it locally. And if I have a strictly totally disconnected space, so that means all the connected components are just of this form. So just collection of points. We have, this is literally functor in the overconvergent sheaves on this X. They are literally just modules over the ring of continuous functions. Maybe pi 0. Okay, because overconvergence forces on every connected component this thing to be just constant, and so the only thing that's left is a bunch of connected components. So that's a pro-finite set. So I literally just have modules over that ring, and now here I have a natural base change factor. I'm not sure if this guy is that nice. Okay, because this ring here is naturally an algebra over that. So I can literally just make it. And here it's useful to have the overconversion version. Without the overconversion, I cannot make this construction. Actually, well, there is a version that works without the overconversion, but it's not as simple. You have to work with it. Yes?
In the second line, tensor OX plus, what's tensor plus?
This one? Yeah. Sorry, it's supposed to be an A. Because I end up in here, so I want to make sure it's clear that I end up. I literally just tensor with the plus version, and then I almost localize. I go to the localized category.
Okay. And also in this definition of overconversion, do you have to account for there being more than one connected component?
What do you mean? I mean, for any map, for any geometric point of X, essentially, or any specialization X, I require some. I mean, this thing here only has one connected component.
But you need this to be. Oh, my bad.
So this thing is literally a chain of. I mean, this is literally like the underlying space of this is literally just spec of C plus, and that's the variation ring. So it's just a chain of points. Okay, maybe it's not literally that. Maybe you remove one point or something. But it's roughly that. Okay. So we have this comparison functor. So we can, for any FP sheaf, we can associate in a quasicoherent sheaf, but this functor is of course not fully faithful. Even in this setting, you see immediately that that cannot be fully faithful because there's far more isomorphism of the string. So what we do is we add an equivariant structure under the Frobenius. Okay. So let me make a full definition. Suppose I have some prefecture space. Let me first define it only for prefectorate. Prefectorate, do that. Now I use a very bold notation.
Just so this probably has some more elementary prototype. in pure characteristic,
Yes.
you have the entire sheet, you can transfer it into structure sheet. And then you get a model of the structure sheet, but it will also be from scratch. And this Frobenius software allows you to construct original entire sheet. And so was it done, for instance, or something like this work by Keaton, maybe by
I think originally is contributed to cuts. Yes, but this might not be, yeah.
You can go backwards.
Right. I guess maybe.
Over the field, it's something. But anyway, it's so it goes back to this characteristic piece.
Yes.
Some sense.
I guess what I'm going to present now is motivated.
Can I make one comment? So it's at least it seems to me, maybe I'm wrong here. It seems to me that there is a big difference in that in characteristic P, so if you're over a field, then this is the result of cats. But here there's but if you're over a valuation ring, you can try to reduce these types of correspondences in characteristic P to valuation rings. But on the other hand, they won't be constant sheaves on an absolutely equally close valuation ring. So at least my impression of is that it has a somewhat different seems somewhat different.
I mean, I don't have to impose this or.
Yeah, well,
Yes,
I mean that would
that's different. That's true. But okay, on the other hand, in schemes you don't have localizations like that anyway. So if you wanted to do it on discrete adic spaces, for example, I guess you would have to make exactly the same kind of.
So I would say that the analogy I suggested is completely misleading.
No.
That it's partially. It's partially.
Partially maybe, yeah. But I think it's a good.
So I understand
good
this is a
intuition.
different story, but it's a first approximation.
I mean, morally, it's very similar idea. Okay, so now I make a protectorate and some solid equalizer. And if I want to introduce Frobenius equivariant structures, I better have my solid equalizer equal P. And now I use bold notation. Okay, just write B of X P. And I mainly use that notation because I don't want to write solid and A's and whatnot all the time. So I define this to be, well, I take this category I had before. Now I take pi equivariant objects. So this is the category of pairs for M is before. I am it's an isomorphism of the fulvic and okay.
So this D doesn't have a substitute.
Yes. I hope that's not too confusing. Sorry. I wanted to have short notation.
Even if it's confusing, we cannot change. So
right. Right. Yeah, it does not have. Yeah, it is not the same as this. But I guess the point of the notation is that I claim it's close. Okay, and we notice something now, namely that this category does not depend on the untold of X, or only depends, only depends on the characteristic P tilde of X, and not on pi. Okay, so that's something you can check. I mean, first of all, that it only depends on the characteristic p tilde. Well, it's basically just because I'm monoid by something that's divisor of p, and that ring only depends on the characteristic p tilde anyway. And the fact that it does not depend on pi is, well, if I choose another pi, if I choose pi to the p or something, it's easy to write down an equivalence of these categories. Because Frobenius maps pi to pi to the p, right? So I get a good notion. You get a V sheaf or hypercompatible V sheaf of categories just on V stack. So also that was just V stacks on the side of perfectory spaces and characteristic P. Okay, so now I've eliminated all these subtleties and stills. So I need to put it together. And well, I claim that this thing is close to étale V sheets. So what is the precise statement?
Question.
Yes.
Is that calculus further equivalent to like the BA box of like the OX factors and the development?
Yes, or you can take the plastic one. And then you have to take.
Then don't you have to.
Yeah.
Also, my question, I guess, is like if it is equivalent to like just OX factors, like without modulo.
Oh,
flats and that.
yes, as a remark. You can also this category. Plus. This is also equivalent to category. Try complete pi modules of the OX factors. And the idea is that if you have a guy in here, then you can take the limit over the previous guy. That's actually very useful to prove the next statement. So here's the theorem. And I guess we can see this as a version of the mod P Riemann-Hilbert correspondence. Okay, so there is an adjunction for every next PV stick. And there is an adjunction, well, in the one direction, it's the Riemann-Hilbert functor, which is the functor I had before. Okay, but implicitly I add the phi module structure on this thing. So that takes me tau over conversion in P sheet. And it sends it to a sheet in this fancy category. And then this has a right adjoint, which is just taking phi invariance. Okay, so it's not so hard to see that there's such an adjunction, but what is the claim now? Such that, well, first of all, the Riemann-Hilbert functor is fully faithful. And induces an equivalence dualizable object. Okay, and you don't know what dualizable means. I mean, it's a notion that you have in any category of the tensor product. And I guess if you don't know what it means, just think of this as being perfect. Okay, so in particular, any local system will be in there.
The dualizable objects exactly going to be like local systems or?
Well, complexes of local systems.
Yeah.
Okay, and what is the main idea of the proof? I will not actually prove this, but basic idea is that, well, both sides satisfy v descent, so by v descent, we can, without loss of randomity, assume that x is strictly totally disconnected. Okay, and then so then it's basically just a profinite collection of sparse CC plus, and then I claim that we can further reduce to I mean, in particular, this category here is very explicit now, right? It's just modules over that ring. And also the other category is very explicit. It's just 5 modules over that ring. And then we can reduce further to by some stored/Cohomology arguments. So the case it is literally just this star CC plus. And now the fact that the Riemann-Hilbert functor is fully faithful is not so hard once you know that taking fine variance limits with fill limits, because well, you literally just have to check that the composition of these functors is the identity. So that's okay. And but the crucial input is this equivalence of dualizable objects. That is a non-trivial statement. And well, now reduce to results by again. Because okay, you can make some further reductions to instead of working with C plus, you can restrict with AC, then you have a vertically closed field, and you have a phi module over that, and these things have been understood classically. And that's where all this really
sorry, just a question. So the over a field is you attributed this to content, why not contents, or is this one time? Yeah, is the attribution to content for the reduction or?
wasn't you the one who studied phi modules in this?
I believe that was originally.
Was it? Okay, maybe class was even earlier. I mean, I'm not talking about schemes over field. I'm literally just like. I think the reference I have in my thesis is a paper. Okay, right. So that's really nice. So we have finally managed to embed the thing that we want to study in something that we can manage because it has some quasi-coherent structure. And well, yes. Now it's time to sketch the construction of the six-factor formalism. Or are there any questions? And so I guess this statement really is an analog of what we had in mind. Okay, so what do we do? Well, fix x. Steps. And now I claim that I can construct 6 functors, and most of them are actually easy to construct. So I can cancel product these are just glue from well, on these categories of modules, I do that for this thing. And then it's formal to just do them along any beat product.
Just one. So the 6 functors are constructed from what? The sheet. So it's not for the original.
Oh, it works. It works for both. It also works for. Sorry. You can do it for this category, or for the phi equivariant. Doesn't matter. but it does not work for this.
Okay, so anyway, here, at this moment, we work not with this F, but with this D without F.
But maybe I shouldn't have thought that.
But anyway, we did it, so let's stick to the notation, otherwise we'll get confused. 26 functors of
And maybe I can make slash the same construction also works. Just for this category without the prime values. And I forgot, I wanted to write on one example, but of like what this category looks like on an actual rigid variety. But maybe since I started with this now, first do the 6 functors, and then you get an example. Okay, so well, the next one is the fullback functor. So that's functor 20. Fine. Well, this one comes just with the fact that this thing is a sheet. And this functor it acts as a sheet, so it must have a sheet functor. Okay, but locally, it is the base change functor. Very big. And just tensor. If you have a map of a finite perfectness, then fullback is just a solid tensor for that. Then, well, the F lower star, the right adjoint the upper star. So that one will compute cohomology at the end. Okay, now come the interesting ones. So, okay, so I want to define the lower shrieks. I define them in 2 cases, namely the proper and the étale case. So if cases. So first, F is étale. Well, in this case, one can check that then so after base change to finite perfected, or even we restricted to the disconnected. X. The associated map. Well, okay, maybe assume also that Y is so I'm localizing. Topological space Y. This map boils down to gives a homologically étale. The associative spectrum. A plus. Okay, in fact, if X is strictly totally disconnected and Y is also finite perfected, then it is a disjoint union of open subsets of X. So any étale map of a restricted to disconnected is an open can be written as disjoint of opens. And also, an open subset in the perfected sense induces an open immersion on these plasma pyrings. So actually, I can just reduce the case that this is an open subset of this. So now I'm back in the solid setting, where now in order to define the lower shriek, I'm literally in the setting of an open immersion in the sense of schemes, and I can literally just take a solid one, lower shrink from solid mathematics.
And and this duality theorem of Clausen and Scholze, which you mentioned last time.
Yes, exactly. On schemes, we have both example formalism for quasicoherent solid sheets. So in particular, for any open inversion of schemes, or even étale map of schemes, I have a lower shrink functor. And I just take that. But in fact, it is literally just left adjoint of the product. So, but this reduction allows me to reduce, to show that this left adjoint exists. And here it is crucial that we take solid. So this will usually end up in actual solid sheets. This will not be as big.
This theorem from solid.
1 second, let me maybe first write this now. So here it's crucial to solid sheets. You're asking where do I find the construction of the lower
No,
shrink?
just
Or
so
solid.
last time you mentioned the theorem.
Yes.
Clausen Scholze that you're using.
Yes.
But I'm a beginner. I want to understand. Probably I have to understand how they do this. This is how they construct the lower shrink. Is it written somewhere?
Yeah, there are the lecture notes by Scholze on advanced mathematics, the very first ones.
Just a moment. Is it in this 2019 notes?
There's well, the thing is, yeah, it is in there, but well, Peter was giving the lecture while working on the theory and writing notes, so don't expect them to be the most easy to understand. It's comprehensively written, but it is essentially in it.
So in this 2019 notes, which I referred to in our private conversation, the correspondence today, I can find this.
You can find the construction of the lower shrinks, at least for stuff that's done at type in Z. I mean, in general, you just base change it there anyways. Right, but I think what he does not really do in there is construct full 600 functors. But the functor is there. And as far as I know, basically every other reference on that more or less refers to this.
Sorry, I can you say what it means by not to be familiar with people?
Oh, okay. I mean, sorry. I can't say, but I would rather just say it's not. And that is fine, I guess. Cohomologically, so well, whenever you have 600 formalism, there's a notion of cohomologically formats in that 600 formalism. And in this case, I mean 600 formalism of solid quasicoherent sheets. And I claim that this map is cohomologically étale. And roughly it just means that upper shrink is the same in that 600. I mean, there's a more sophisticated definition that looks a bit better than just saying that. But,
There's some clarification here. When you say F is étale, that means F is étale and representable. Is that? I mean, representability is part of. So based.
oh yeah, sorry. Yes. So being an étale map is the definition of Scholze in the setting of small b stacks, and it is in particular representable. Yeah. So whenever you base change to a strictly disconnected space, it needs to be or even protected space. I guess it needs to be an étale map of protected spaces. Yeah, I guess that's maybe a little bit different to what people tend to do in algebraic geometry.
Like like BG to a point is not.
Yes. But it will be cohomologically étale later. Not étale methods. Okay, but that is proper. So what does proper mean? Well, this means quasi-compact. Or but maybe I don't write down the exact definition. There is a definition of proper maps of these stacks. Roughly just says quasi-compact universally closed. Forgot one. But the usual ones are done. Then okay, and maybe plus bounded on cohomology. And we need to make a small extra assumption. Maybe let's just ignore that. Then I define f of lower shrink. Okay, in this boundedness assumption, I need to make sure that this thing actually produces Colmez. That map is too big. So this is basically some. Well, this goes in the direction of finite type assumptions, but it's I guess weaker. But yeah, it puts some finiteness hypothesis on it.
But proper map does not have to be represented.
No, proper maps don't need to be represented. Okay. So this allows me now to define lower shrink functor. I can define lower shrink for all f that v locally on x and locally on the space y vector into cases 1 and 2. Okay, so roughly I want something that is locally at least compactifiable, and these maps are called BDCS. That's the best name I could come up with. It stands for, so BD stands for bounded, so that's trying to capture this boundedness hypothesis I have here. C stands for compactifiable, and S stands for spatial, which is some technical nonsense you have to deal with in this diamond setting, which I do not really want to remark on. But it's more or less exactly this.
Can you write this?
So BD, okay. So BD is bounded equal dimension. The C is compactifiable. And the S is spatial. The spatial is roughly the statement that the underlying spaces are spectral. I want to make this assumption. But let me, okay, first of all, then for all F BDCS, we define the F of a shrink as the right shot. The F-lower shrink. Okay, and let me give you one example of BDCS maps. Every map of rigid varieties over some fixed base is BDCS. So as long as you stay in rigid geometry, there's no restriction at all. You just have three functors there. Okay, so this BDCS assumption only comes into play if you deal with actual V stacks. I mean, because a remarkable fact maybe in all of this, that's very remarkable in Scholze's theory, we do not pose any assumptions on our V-stacks, right? Just like an arbitrary V-stack. Like in algebraic geometry, usually we work with, I don't know, Artin stacks or algebraic stacks, right? They put some restrictions on the stacks. Here we don't have to, just. But maybe then it's not surprising that if I want to define a lower streak, I have to put some assumptions on. No. Well, I mean, okay, locally I want it to be. This compactifiable includes separated, but this only needs to hold locally. I mean, like if you have a map of rigid spaces, every map of rigid spaces is locally separated, so that's fine. Okay, maybe I should, yeah. Well, I should say to actually define these lower shrieks for non-separated maps, there are some technical issues that you have to get around with. And yeah, I didn't really want to talk about like this theory of 6 functors that's kind of secretly behind all of this. But the problem you have, like if I define the lower shriek like that, and it's not so clear why that is functorial, right? First of all,
what do you need here by the 6 functors?
Well, there is an abstract definition.
I see. So there is a certain abstract theory of the all possible or conceivable 6 functor formalisms. And without this, many things are not clear. For instance, if you define F separate with étale and proper, you need to check a lot of compatibilities. And
I would say even infinitely many, because this is
what
I mean, I work implicitly with infinity categories here, so
and this makes it especially hard. But even without infinity categories, I really remember that people who wrote this cheating or somehow struggled with it.
Yes.
And fortunately for us, somebody developed a kind of abstract theory which tells you probably that under certain abstractions, right? This is sort of.
I mean,
it tells us what you really have to check.
Right.
So maybe in particular, so part of the machinery is showing that like 2 different factorizations of a map into like a proper and étale that they give you canonically the same lower shrink.
Right, but it turns out, I mean, this is part of my thesis, but I basically just extract from the literature what other people have done and write it down, maybe slightly more conceptually, but right, I mean, there is the abstract theory of 6 functor formalisms reduces checking this to actual checking a natural map of, well, if you have, like, at the end, the only check that a natural map of functors is an isomorphism. For maybe any factorization, maybe, okay, I don't really want to go into that, but yeah, I mean, part of the stuff I do in my thesis is working out how to construct 6 functor formalisms properly, in the sense that checking all these things is done somehow in an abstract, formal way. But as I said, this is based on previous work. I mean, I basically just extract. Right, and using that, you can check this, and once you manage to make this independent of all choices, it's not hard to extend this to non-separated maps. Because once F lower shriek is functorial in F, basically you just take an open cover and you take a colimit over that open cover. But for that, you really need this to be functorial and even like in an infinity categorical sense. So I really need to check that all the higher homotopies and blah, 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 they all work. Okay. So there's some magic behind the scenes.
Sorry, so basically, the fact that we don't need this separatedness is from the fact that to define a flow shriek, we can also work be locally on the source, right? And
well, not be locally, but at least, well, I guess in general,
only locally on.
I guess you can always work cohomologically smooth locally. That's, I guess, maybe the best
like
I can give you, but
in some way locally on the source,
yes,
right?
yes,
Which is in contrary to like how you define the cohomology of complex separating, like étale cohomology.
Right, it's like classically, but if you don't have this heavy machine, and you're forced to do it ad hoc somehow, I guess you're usually restricted to the separated case.
Mhm.
Okay, so theorem of construction. Uses a six-functor formalism. i.e. with all expected compatibilities. Yeah, so I guess maybe the most important ones, proper base change on the projection formula. So it is a six-functor formalism in as fancy way as you want to say, essentially. And the fact that I can make it in such a fancy way will actually become a bit important later. But so with the six-functor formalism, I do not make any claims about Poincaré here, as you might notice. And the reason is that this will be the next chapter. The reason is that Poincaré is not an intrinsic property of the six-functor formalism. And also that in the category of V-stacks, there's no good notion of smooth maps, so it doesn't even make sense to define Poincaré. Okay. Let's talk about smoothness. Now I guess you will finally see an example of this category. That's the only one I can compute, actually. So I said there's no definition of smoothness. So I cannot write down a theorem like every smooth map satisfies Poincaré duality in the six-functor formalism. But instead, what I can do is I can define a map to be cohomologically smooth if it does satisfy Poincaré duality. Okay, so a map F in V stack is p-homologically smooth. If the following two properties are true. Well, first of all, there's a natural map. But first of all, I can define the dualizing complex of F, which I just define as F upper shriek of P. So this is an element P of Y comma FP. And maybe, okay, I guess I use slight abuse of notation here. I view FP as an element in here via the Riemann-Hilbert correspondence. And I mainly do that because I don't want to write OX plus one P all the time. I guess implicitly, this is the sheet OX plus one pi with a natural pi function. Again, the first condition is that this dualizing complex is invertible. And in other words, there is another object omega F inverse such that tensoring then is isomorphic to the unit. And the natural map F upper star tensor. This natural map is an isomorphism. Okay, and unfortunately, it's not enough to just ask for these two, because this thing a priori is not necessarily stable in a base change. So I ask the same that is true. The base change. Okay. And
Question. So when you say the natural map, this is something that comes from for any six functor formula.
Right. So this is, I mean, this is the right adjoint, right? So mapping to here is the same as mapping from a lower shrink of this guy to unit. But now by projection formula, I can basically like, maybe it's an exercise, but there's an natural map. Okay, actually, like nowadays, I wouldn't formulate it that way anymore. Using the abstract theory of six functor formalisms, I think there's a better definition, but that's the fastest one to write down without talking about two categories. So I guess I'll stick to this. And then, okay, it's immediately clear. And I just phrase this here quickly. So smoothness or p-homological smoothness is stable under composition, phase change, and
What's the role of p-cohomologically, because we're dealing with
yes,
FP.
right, exactly. In Scholze's work on diamonds, there's an analogous definition for L. They literally just takes étale sheaves and shows that they have. I mean, they have six functor formalism. He just asks for those to be smooth in that sense. So being smooth, stable under composition and base change, and local, V local on the target. And étale local on source. Okay, these are also statements that hold in any six functor formalism. And there's completely abstract proof. And maybe let me now state my theorem here, and I think we're having a break soon, right? So maybe let me just state this theorem and then let's have a quick break. So that F apply to X, we a smooth map of analytic adic spaces over QP. Okay, so this can be, for example, analytic varieties. Sorry, rigid varieties over any extended. But I guess analytic adic spaces are a bit more general, but I guess rigid spaces maybe is the most important one. Of pure dimension D. Then F is equimologically smooth. And I can identify the dualizing complex to be just Fp shifted by 2D and then tape twisted by D. Okay, and again, this is the simplification. This omega F a priori is an object in here. But yeah, I think this notation is easier to read. And pass it to right. Okay, I guess maybe it's good to have a break now, and then after the break, I sketch how you can prove this. Okay. Yeah, so before I come to the proof, I keep promising examples, so maybe I should write down 2 examples. One of them is actually important for the proof. Maybe those. Okay, so examples. So this is more like examples of the theory and not so much of that theorem. Sorry. Okay. The first one, I guess I should say that because I was actually asked this. Great. You can recover the usual theory of the usual pi gamma correspondence of pi gamma modules and Galler representations. Yes, I want to briefly mention that. So you take well, take X to be star QP, given as a V stack, so I can write this as, well, everything is given by taking the perfected covers. So I take a cyclotomic extension, right? Just a join all conjoined through its community. Okay, and then this thing as a V stack, I mean, this is a torsor with respect to the usual group gamma, which is the P. So I mod that out, I get star QP. But now what do I get? Well, the Riemann-Hilbert correspondence says that p-adic X P over convergent, and that's to P of X and P. So let's compute both sides. Well, here I'm literally just taking a tile of P sheaves on stack P, so that is just modules Galois representation. So that's the category of smooth Galois representations on P vector spaces. And what's this? Well, by descent, I can write an object here as an object in here together with action of gamma. But this guy's perfected, and on a perfected, I know what this category is. It's literally just the category of modules, right? So I only mod out by gamma. So what do I get? Well, I get the category of high gamma modules. Over. Okay, now here are some choices you can make. How you want to write this? I guess maybe in the way I usually wrote this. Modules over this ring, but maybe almost. But okay, as I said earlier, you can also take the completion. So this is essentially the category. And now the Riemann-Hilbert correspondence gives you an embedding of this, and it identifies dualizable objects on both sides. So if you restrict to finite dimensional stuff, you get a that is one incarnation of the usual by gamma. And more importantly, for more importantly, yeah, in this case, there's destruction on both sides. In general, there's general no destruction on that thing. And the problem is that this base change here is not the exact. Basically, always, like even if you have an open immersion, like even if you put this open immersion of schemes, the solid base change is not the exact. So that's something you have to deal with in solid mechanics. So there's no hope to work with a billion categories. I mean, it's not too bad. I mean, the base change still has 4-dimension 1. So the first thing it gets is like one more term to the left. But I mean, you can define a T structure because defining T structures is somehow usual. You just specify the connected objects, and then you say everything is presentable, and you have T structure. But I don't think it's a very good one in this case. Okay. So the extra example that we need for the Smith case is that of X torus times T inverse, then this category is the category of smooth ZP maybe take was one representations. Sorry. On O C on T and T plus minus 1 over 2 modules. Okay, and then I guess I have to take solid almost. And semi-linear. Okay. I mean, what is the idea? You cover that space by the prefectured torus that has prefectured and has a ring, this guy. And hence the module on this guy is, well, by the descent datum is exactly this representation of this. So you just take module on the prefectured torus together with this something. Okay. This is the only concrete example I can write down in rigid geometry, but it turns out that's all you need. Because if you want to check that something is smooth, locally everything is a torus. So it's enough to understand this guy. Okay, and that's also the idea of the proof of the theorem. Concrete description of what? Say again.
I think they essentially reach it.
Yeah, to the side, exit.
Just to check, that kind of question is like basically related to whether you have enough C variables.
I guess, yeah. I mean, at the end, the Riemann-Hilbert person, like the proof of Riemann-Hilbert boiled down to checking that over algebraically closed field you always have.
Yeah.
So here, I guess.
So it might be that you have a distinct since you're doing something mathematically, you can imagine objects will actually be some kind of shift operator or something.
Right. I mean, you certainly can always take something like a free phi module. That will never lie in there. So this is always bigger as étale sheets because you always have the free phi module and that will never lie in there. Right, but I'm not aware of any good description of the essential. Well, only the second one. First was just, yeah, I thought it was a nice example.
Yeah.
Okay, so how does the theorem work? Well, by the lemma, can reduce to x just star a plus totally disconnected or even strictly totally disconnected. So for this statement, not of course, but for the first part of the statement, can reduce locally, but x is strictly totally disconnected, and y is just a relative torus, which is a prime t plus minus a plus prime t plus minus. Okay. So the whole statement of pro-étale has now been reduced to the very complete example of the torus. And in this case, you know exactly what these categories are, right? So computations are not that difficult. Maybe I still roughly sketch the idea. And then, so what we need to prove is pro-étale, and it follows from the statements. Follows from the above example. So this is example 2, which gives us an explicit description of all the categories here. Using, well, the first one is pro-étale or the p-cohomology. And so the ZP is p-adic group of dimension 1. It has pro-étale, and like the cohomological dimension of this guy is 1. So this gives the shift by 1. And then I need another duality namely functor for quasicoherent sheaves. On spec A plus rank E plus minus and while combining both of these, and the functor, this guy also has dimension 1 over the base, which is just like plus not B. So this gives a shift by 1, this gives a shift by 1, you end up with a shift by 2. That's essentially it. Okay, so this proves that at this cohomology is smooth.
Poincaré for the quadrilaterals, it's like same kind of definite set duality, you have the solid universe.
Here I mean the solid universe, yeah. I guess, I mean, if A was Noetherian, then probably you can also refer to the sex project, but and this guy a priori is far from being Noetherian, so I would be careful. But yeah, the solid framework is of course very solid. Okay, so that is the cohomology smooth. So maybe also let me say that in this argument is basically due to context. Okay, because if you look at what's actually going on here is, well, I have a nice enough space, I choose a formal model and I prove functor-étality on the rigid variety by passing through the formal model. And I said, I think at the beginning of last talk, that faulting more or less had a proof of functor-étality if I have a smooth formal model. And basically his idea is, well, he did this computation. If you have a smooth formal model, then locally your model looks like this. And well, you're done. So this is the essential computation if you have a smooth formal model. But the point is that because now everything works on the rigid fiber, you can really, on the rigid fiber, reduce to that case. Now it's that's it. Okay. And
So it's Poincaré like for C coefficients, which is geometry.
I mean, homology of ZP is just to take the complex with. Yes, sorry.
Oh, C.
Yes. Sorry. Yeah.
Yeah, sorry, I thought.
I mean, ZP group homology is very
Right.
little. Okay. Okay, now we need to identify the dualizing complex. So to identify this omega f, we use a standard technique. I guess nowadays it's a standard technique called deformation normal cone. And the idea is roughly to, well, reduce computing the omega f1 arbitrary map to reducing it for the zero section of the vector bundle. And that essentially reduces to computing it for the zero section of just a band from 0 to A1. And then you're more or less in this situation. But to make this work, maybe I should say here it's crucial that there is no non-trivial notable or field persistent on E1. Okay, because well, the idea of this deformation of the normal cone is to take a deformation of P1, and I might need to make sure that all the stocks are the same. I don't want to go too much into details. I just wanted to say that because for this to hold, it's really important now that I work in this phi module category. Because in phi modules, there's nothing interesting I can do on a local system. But if I did not impose the phi module condition, then invertible objects in that category without the phi module condition, they are weird. They're actually really weird. Like even on a geometric point, you can have non-trivial invertible objects in this category without the prime modules. So this is basically the main reason why I introduced the prime modules in the first place. Like for the most part of my thesis, I just worked without the prime modules. Everything I said so far works without, but here it was crucial that I have this high action.
I guess I just have a question about, so is it correct, so in particular, you want a map from between those two objects, right? So you want to produce a map between
those two?
Yes.
No, I mean there is no natural map. That's no problem.
You're saying it's not, there's not a natural map, let's say, so like, or really a map from F lower 3 of FT shifted by D.
There's no. I mean, I produced one at the end, but up here there's no. Like the thing you really do is you look at all maps, like all apps at once, and well, you know that basically for every app you have this, so you have a functor on all maps to sheets, and then you use functoriality of that to reduce further and further down to saying that such a functor under some properties is given by just knowing what it does on one object, and that. Okay, this is a standard technique. I think classically identifying these dualizing objects is quite hard because you need to construct these. You need to build a map between both sides. I guess that is usually what people call trace maps or whatever, right? These are hard to construct if you do it by hand. But I claim that once I have a functor formalism, there's a standard technique how you can do it, and that technique basically works, I guess, most examples. So every example I know at least. And it's even formalized in a paper by Zavila. Axiomatizes what exactly you need.
So yours is a certain trick.
Yes, I think it goes back to Brooklyn, maybe. I think he used it somewhere in SGA, I don't know. But I think it was made like the hype came, I think, from Dustin who found that and promoted it.
Can you write some names like references?
So I think this is originally, I might be wrong. I think it was Berkeley, or at least his school. Maybe someone else from that school. Yeah, I'm a bit reluctant to write that as I don't know.
Yes, but this will not allow us to find the
rest. Okay, so if you want a reference.
Yes, something which could enable us to find a reference in a whole simple situation.
I'm just going to look at Jacquet-Langlands' paper. I think it's called something like concrete reality revisited. I think it's something like this. You should find it if you know. I mean, he does some more things in there, but I think in particular the arguments. And of course, I mean, I have this argument by physics most of the time. But there I use specifically. Yes.
It's a problem of finding the argument. So this is a good reference because it's.
I think it's somewhere in chapter 3.10. And some theorem at the end. And I think I make a remark after the theorem where I try to extract the essential parts. Yeah, but maybe it's better to look at Boatman's paper. Makes it more abstract. That's more applicable to most situations. But yeah, I guess the idea to apply it in that way is to destination. I think it solves a lot of issues that people originally had. Okay. So let me write down one corollary. I kind of basically I've proven now the concrete statement. And yes. I also claim, I mean, to get this, I guess you still need some comparison between a p-cohomology and the cohomology that I have in this theory. But there's what a corollary from the smoothness part. And it says that F is a proper smooth map of rigid analytic spaces. Over QP. Then for every perfect local system. So perfect means complex of local systems. Y. We know that, well, first of all, push forward. This is how, well, I claim it is lies and X. Like it's an actual enthalpy, sorry. So this is the push forward. Categorical properties. And this is perfect. And okay, the way I write it here, I make too many implicit identifications, I guess. So implicitly, you can choose either F lower star and it's the same way. So you can take the étale, usual étale derived push forward, or you can take the push forward of this category, and it gives you this. And the computer. Maybe I'll just call it F étale. In other words, in this case, everything is nice. The lower star just restricts to a functor. And I guess this is like the usual statement that we expect now that the proper map became a proper smooth. Then the derived push forward, but if you take a local system on top, then all the RI F lower star of that thing will again be local systems. And this result is not new, this has been proved by Scholze, I think. Probably this generality. But I claim that out of this, the following just falls out. And I know that F is smooth, so that implies that F of a shrink preserves full limits. Smooth. Okay, but if the right adjoint of something preserves full limits, it means that the left adjoint of something exists. So star preserves. Okay. And also discrete objects, which is true for any problem. Hansen. Polarizable objects. Okay, now we finished by as I recall correspondence, which tells us that as soon as we have a dualizable object on either side, they must like dualizable objects on both sides of the same.
So the shape of the compact and discrete objects are the same as dualizable objects?
Yes. Okay. Yeah, that is okay, maybe only under some quasi-convex assumptions.
That calculate also implicitly prove the FA star part of the statement too.
Yes.
Or the FA star.
Although what's always true. Maybe that also answers a little bit question about me last time. I mean, what you always can do, if you take the F-lower star of, I don't know, your favorite G, compute it in this example form is constructed. You then take time variance, and that will always give you the naive F-lower star. That is just true because in passing to left adjoints, that's just saying that we remove it to use with space change, and that is one change. And yeah, so I guess implicitly I plug this in as well.
Another question. So further in this primitive comparison, is that going to be the templates?
This is primitive comparison templates. Yes.
But I mean, even if X is a point, then this is a different argument.
Yes, the argument is completely different. It does not. I mean, Scholze's argument is quite subtle, even for the absolute setting. I guess at the end it boils down to computation on this, and then he has to somewhat globalize. I mean, the problem is always that you have to use smoothness and properness, right? And the cool thing is that with this functor formalism, functor formalisms give you a very nice way of dealing with situations which are both smooth and proper, because you can understand both properties globally now. Like smoothness just says that this guy is nice, properness says that this guy is nice. That is to say.
So I mean, in particular, I think part of Clausen's result was that if you have a proper rigid-analytic space, over C, then it's a tall cohomology, it might be a tall cohomology, it's finite dimensional.
Yes.
And that's something that follows, if you're saying it follows immediately from the same place.
Well, at least if it's also smooth, which is, I guess, the original statement. If it's only proper, then I guess you have to do a similar thing as Scholze does in a later paper, where he uses resolution of singularities. Yeah, in the smooth case, it's completely proper. Right. Once you have the machine. Okay, so this also now recovers pro-étale. And not only that, I mean, you get any relative version that you like, right? You can take smooth map, take a local system up top, you can push down. You can dualize downstairs, that's the same as first dualizing upstairs, then pushing, right? Like the usual statement that you would want to like. They just, I mean, this just tells you that in the proper smooth situation, the usually Cauchys behave like a 600. Okay.
So in some sense, from your perspective, long ago, the argument had a sort of version of, like a more naive version of the Gamma modules to try and compute say p-adic cohomology and p-adic geometry and so on. And I guess this probably would like encapsulate or whatever.
Well, this is
Along those
actually
lines.
right?
Yeah, well, these are ground I think people probably like go to
Yes, sure. Yeah, as long as you only want to compute cohomology itself, yeah, I guess.
But in some sense, like concretely, all the things are being computed by like Gamma module.
I guess. Well, the gamma. Well, if you do it in the arithmetic setting, yes.
Well, here there's also some kind of a gamma.
Okay. Yeah, I guess there's also gamma. Yeah, I guess implicitly all of this goes in, and somehow this example formalism just gives you a very nice way to handle all the like gluing that you would have to do. Right? Yeah. If you try to do, I mean, you can also try to extend, for example, this machine to more general formal models, and that's what Zabulan does. It is possible, but it's very subtle, right? The model is not smooth. Like finding smooth models is a very subtle business, and gluing all these things together and constructing these trace maps and so on, that's all very subtle. And the fact that we can do it without all of that, I guess that's the main point of my thesis. You can work directly on the fiber. Okay, so this covers the pro-étale, and now I promised last time some implications. I'll find my notes for that. Okay, I have some applications written on the board, but maybe. Okay, so this is primitive comparison, right? In the most general form that you can maybe imagine. And I wanted to present one application, Jacquet-Langlands. Then if there's time, I also wanted to maybe touch a little bit on how you can do the same for p coefficients. Turns out to be surprisingly interesting field as well, beyond p version. But maybe let's first talk about Jacquet-Langlands. Okay, so now let's pick some settings so that G be just yield to P. Just fix GL to QP because I'm lazy. I guess you can do GLN over an arbitrary extension of QP as well. But I'm not that good with computation, so that's the only case I actually understand. To some extent. And B, the comparing algebra. Over QP. And then I think there's a classical theorem called the Jacquet-Langlands works on this. Says that natural projection magnets going from something like reducible square-level representations. So this is the complex setting now. So these are complex. Okay, and this is compatible. I mean, it's compatible with a lot of things, but I think that's compatible with quantum mediums. And I guess the natural question you can ask is if there's a similar analog in the p setting. So instead of, okay, first of all, for coefficient, this also works. So I guess the next question is, can I do it with what p representation? Final p coefficients and smooth representations. Okay, and I think this has been studied maybe by several people, but one person constructed such a functor at least, is Scholze. So let me maybe sketch what Scholze does. So he considers infinite level. No. Unfortunately, nothing like that. No. But a functor.
At least a function of one, but not an equal.
Yes.
It only be not here.
And that functor, as far as I know, is not that well understood. But the application I want to give, I mean, Scholze constructs the functor. And the application I want to give is, well, learn some new stuff about the functor. So we consider the infinite level Lubin-Tate tower, or Lubin-Tate space. So call this infinity. Okay, so if you're not familiar with that, I mean, that is okay. That is the space that lives over CP, I guess, if you base change it. and it parameterizes, well, you fix your favorite formal group of height 2 and dimension 1 over FP. This guy parameterizes the formation of that thing to OCP. And the level means that I add a level structure where I fix the tape module, fix the basis of the tape module. Okay, and the cool thing about this space is that there's two groups acting on this, maybe G. Oh, did I write D cross? Yeah. So there's two groups acting on this, maybe G and D cross. Well, D happens to be just the anamorphisms of the formal group, so that is quite easy to act. And G acts by acting on the level structure. And well, then this guy has a map to P1, and this map is G equivariant. Sorry, it's a G torser. So, and in particular, it also it's equivariant for an action of D cross on P1. And so what Scholze does is to smooth G right I, he constructs QP. QP. So there's, I mean, you also have, I guess, the critical space. But then here you have GO2 ZP. And then you can also go to P1 by GO2 QP torso. And this may sound weird, because P1 is supposed to be simply connected, but in rigid geometry, weird things happen. So to smooth G representation pi, we construct, Scholze constructs a sheaf F pi on P1. Okay. Well, using the G action, uses the G action to descend it from, well, basically just pull it down up here. You descend it using the G action, you get a sheaf right here. And then he defines Jacquet-Langlands functor of pi to be the cohomology P1, which is F pi. Okay, so this now lives in smooth representations of D cross, this D cross layers. And so well, you can write on the functor. Yes. Yes. So yeah, so I can also continue to write. I'll continue writing here.
Sorry, which paper is the reference for this?
This is. Sorry, I'll move it down again in a second. So this is the paper Scholze. Something with looping tape.
On the cohomology of the looping tape column. I think if you Google Scholze and looping tape.
Yeah, usually I just Google Scholze and looping tape and I find. This is the paper by Scholze. Yeah. I mean, it's also quite old actually. And in particular, back then he didn't have diamonds and so on. So the stuff, well, he works very explicitly with equivariant rigid varieties and so on. Okay, and I mean, what Scholze, I guess one of the main results that Scholze constructs there is that this is compatible with some other constructions you can make out of patching using global versions with like the Langlands functor. I don't worry too much about that because I only want to have a local thing. And also what Scholze shows is that if you plug in an admissible representation, then what you will get out is also an admissible representation. That's also one of the main results. But there's, I think beyond that, there's well, it's not so easy to prove much beyond that. Like, for example, when is this thing 0, or maybe does it vanish in some degrees, or maybe is it maybe situated in only 1 degree? I mean, that would be the optimal case, right? If I plug in a representation, I don't want a complex out. I want a representation out. So these kinds of questions are unanswered, and they're still unanswered. But we can. Well, with the machine, I can now get a very clean and easy proof of some of the statements in Scholze and something new. So this is joined with David Hansen. And it says the following. So first of all, this Jacquet-Langlands reserves admissible equations. In other words, if you plug in something admissible, you will get out something admissible. And well, in the derived category, I just mean finite complex of admissible representations. Okay, this was proved by Scholze, but he uses some proof technique that is similar to the primitive comparison theorem, but in this setting, so you had to reprove everything, I guess. And some use with say derived contravariants or duals. Of admissible representations. Well, the fact that it can be used with derived contravariants or derived duals is also a useful property, because if you, I don't know, if you happen to know that some part of this cohomology vanishes, and you know that self-dual or something, that also the other parts vanish. You can play these kinds of games, and in the paper we play these kinds of games. But please don't ask me about that, because. Huh? Yeah. Yes, I guess. I mean, yeah. Well, it's literally just taking the dual and the derived category, I guess. I guess it was first studied by Colmez, maybe, but yeah. But I mean, in terms of derived categories, it's literally just take the dual, derived dual. Okay, here's the sketch. And I claim that the argument is actually very simple. So I consider the space X, which is this infinite space, and I just model both actions. And then it's known that this thing, if I model the d-cross action, okay, I haven't said that before, but it also has a period map to d-cross. The d-cross torsor going to Greenfield space. So if I first model d-cross, I get Greenfield upper half plane, and then I model G, and I can also, by the thing I wrote there, I can also identify the d1 model d-cross. And now this maps to d-cross, and this maps to the classifying state of G. And let me call this map G, this map F. And then we see that this map is smooth. This map here is proper and smooth. And now this defines a functor from the category. And here, category in here, and well, the functor is literally just taking pullback along F and then G. And if you look closely at what Peter does, that's exactly his functor. Well, at least, he does it on étale sheets, basically, but we reinterpret this now, this here. And, well, the thing is, because this guy is smooth and this guy is proper and cohomologically smooth, and proper and smooth, it's easy to see that that functor actually can use this duality. Just play around with formulas. Okay, but we want to have a statement for admissible representation. And now I claim that this is something I do not want to talk about here because point of this was talk about this particular six-functor formalism. But whenever you have a six-functor formalism, there is a formal definition of what an admissible object in that six-functor formalism is. And it is formal that the functor restricts to an equivalent to a functor on admissible objects, which still commutes with contravenience. And I know it's a bit bad that I don't really define that here because well, the definition is not that easy, but it is completely formal, and you can check. And also the fact that this factor is completely formal. And now the only thing you need to check is that this is the same as the category of smooth admissible tree representations. This is the category of cross representations. And well, where does this come from? Well, I mean, these guys certainly embed into up here via the Riemann Hilbert functor. So you only need to check that admissibility is exactly the same condition for both settings. And okay, that's not hard. Once I tell you what the definition of admissibility here is, it's not hard to check that something is admissible in here, but only if it lies in here and from an admissible representation. Okay. So it restricts to this functor. This is the Jacquet-Langlands functor. And well, that's essentially. Okay, and this is a statement that people have tried to prove before, commutativity with quantum-convenience, and as far as I know, it's really hard to do without this. Although here you have like another one-line proof. Okay, and maybe as a side remark, I guess you should see. I mean, with now the modern development of Scholze geometrization of Langlands and so on, I guess you should see this as a baby case of some hacker action in the modern setting. And of course, like one idea of the pieces of the stuff that I do with these is to apply all of this Scholze setting to study FP sheaves on Bungie and try to compare them maybe to sheaves in the embedded G stack and so on. But okay, I guess that's the only concrete thing I can say about that. Okay, I guess I have 5 minutes left, so maybe I can very roughly